the operator you're looking at in the index. So I'm going to give a couple of examples. Yeah. Yes. It's, you want, should I write that down? Yeah, it's a polynomial that is closed. I mean, the characteristics of it are that it can be, in principle, any polynomial that is closed and that also is gauge invariant under a gauge transform. Those are the two things that define it at this stage of the game. So, where was I? Okay, so the index theorem, which is still not obvious, but I'll state what it is. I'm not going to prove it. It's given by this quantity here. One of the pieces is manipulated to give you that, and the other piece is manipulated to give you that. And that's what you have. So the breaking into two pieces is due to this constant. And I've got the arithmetic on the sheet here. I've worked it all out if you want to see the details. But I would I'd rather get to the point. df lambda is equal to f lambda a lambda. So df lambda to the n minus 2 is just the same commutator. So delta f lambda delta lambda is dA plus a with a lambda, and so that bit of arithmetic here forces this equality I'm looking at now. So that forces, if you use this in here to get rid of some terms, that forces this equality, which is the symmetry of d delta f lambda minus dA from that thing at the bottom times f lambda to the n minus 2, and the other one is plus the symmetry of d a and d f lambda n minus 2. So that's another intermediate stage in this somewhat laborious arithmetical exercise. But where you end up with that, the object of the game is to figure out what that omega 2n minus 2 structure is. And so it's going to equal, remember, the d is here, so that d pulls out. So this whole thing is going to be that omega, let me just write it in, it's omega 2n minus 2, 1, just to remind you what that was. So that stuff, this term here is that thing. The first term comes into play as well. And when you put this together with that, let me just write out the result. It is not a priori obvious. It's n times n minus 1 times the integral of d lambda of lambda minus 1 times the symmetry of d, with d acting on the symmetrization of A with f to the n minus. So it actually compresses down after some arithmetic to that form. So let me just write out what it looks like for n equals 3. For n equals 3, we have omega 1, 4. 6 minus 2 is 4. It'll be 3 times 2, 3 times 2, times the integral from 0 to 1 d lambda, lambda take away 1, times the symmetry of d, and times, since that's just one factor, it's just this times this, lambda dA plus lambda squared A squared. And now all of these integrals can be done. You get 3 times 2 over minus 6 times the symmetry of d of dA, sorry, of, careful, d of A dA plus 1/2 A cubed, and that is the non-abelian anomaly that we looked at, I guess. So in other words, the reason why I pushed through this is I wanted to get to that. Oh, I think I have to stop at 4. It's actually 4. So maybe that's a bit too fast. I have suppressed arithmetical steps to go from here to there to there. Obviously, you're not going to see that. I've written down the main point, but if you want to work through it, it's a bit of work, but it's not terrible, horrible work. And I can let Dan and Tibra, well, I believe they have a copy, and I'm happy to let you guys see this to work through the arithmetic. But it is just arithmetic with gauge covariant derivatives and symmetries and so on that get you to this point. So what is the point? The point is that the gauge variation of the abelian anomaly is the d of the non-abelian anomaly. So this is the relationship between the two. If you have an abelian anomaly in a gauge theory, suppose you have a gauge theory and you look at its chiral transformations, the massless gauge theory, you look at its chiral transformations, you will in general get an abelian anomaly if you're in an even number of dimensions. The gauge variation of that anomaly is the d of the non-abelian anomaly in 2 fewer dimensions. Delta of omega 2n minus 1 is the d of omega 2n minus 2. And the exponent 0 means there's no dependence on a gauge parameter. The exponent 1 means there's a linear